So we're going to be considering anisotropy and isotropy. Anisotropy and isotropy. So we're going to be looking at the anisotropic properties and isotropic properties of crystalline solids and amorphous solids. To begin with, let's start with crystalline solids. So these materials are anisotropic, meaning that the physical properties vary depending on the direction of property. So let me put it here at the physical properties. Don't forget that earlier I stated that for these crystalline solids, they are highly organized. They are highly organized, while that of amorphous substances are not organized. They are not organized. That is, they have no shape, from the word amorphous. Now, let's look at that of amorphous solids. Now, crystalline solids are anisotropic. And what does that mean? It means that their physical properties vary. It varies. Now, but for amorphous solids, they are what? Isotropic. And what does this mean? It means they have uniform properties in all directions. They have uniform property in all directions. Uniform properties in all directions. Now, let's consider crystal structures. That is face-centered and body-centered cubic. So this is another topic entirely, another subtopic. And body-centered cubic. Now, crystalline solids can adopt various lattice structures with face-centered cubic FCC and body-centered cubic BCC. Now, these are the two prevalent types of crystal structures that we have. Let's begin with face-centered structure. But before we even start with this, I know it is something that is very, very common around most as soon as but then I want us to simplify this. I'm going to give you a diagram and then I'm going to give you a definition of terms. But to begin with, let's start with simple cubic unit cell. Simple cubic unit cell. Now, later on, you understand why I want us to start with simple cubic unit cell. And now, what does this have to say? Atoms are positioned at each corner of the cube with 1 point atom per unit cell. Atoms are positioned at each corner. Now, let me write it before I draw my diagram. What does this mean? So, we are talking about cube. So I'm going to draw a cube. So, atoms are positioned at each corner. Each corner, what does that mean? Each corner. Each corner. Each corner. Each corner. Now, if you count it, how many is this going to give us? This is 1, 2, 3, 4, 5, 6, 7, 8. We have 8 of them. However, these 8 are being shared. One of these is equal to what? Since they are being shared, one of these is equal to what? 1 over 8. And now, if you know, if you are following well, I counted 8 earlier. So that means 1 of these times 8. What is going to give us? All things. It's going to give us what? 1. with one atom per unit cell. Now, and then this structure is what? It has a low packing efficiency. It has a low packing efficiency. Now, let's move to body-centered cube, BCC. This is number 2. This is number 1. Body-centered cube. Atoms are located at each corner and one single atom at the center of the cube. Now, similar to this, that was why I told you I was going to draw a similar, a simple cubic unit atom for you to understand how this works. So this is a simple cubic unit cell. A simple cubic unit cell. So without a body centered, it is quite different from this. The difference is just that there is an atom, just one atom that is positioned at the center. So what does that mean? For this one also, atoms are positioned at the center, at the corners. At the corners, and one atom. This is just a basic definition. So how does this work? We have it like this. Then one at the center. So this is how it works. I hope you are following. With one at the center. So if we're going to calculate this, what is it going to give us? We have 1 over 8 times 8 of this plus 1, this one atom at the center. What's going to give us? It's going to give us what? 1 plus 1. That's 2 atoms. Now, for these ones, they have higher efficiency, higher packing efficiency. They have higher packing efficiency. So, body-centered cubic have higher packing efficiency compared to that of simple cubic unit cell. Now, let's look at the third one, which is face center. So, number 3, we have face centered. That is what? FCC. FCC. Face center. Now, this has atoms positioned at the corner of each of the at the corners, right? So we have atoms are positioned at the corner. And now there's a clause to this. There is one. We also have one atom at the center of each. At the center of each unit cell, each faces. At the center of each faces. So at the center of each faces, we have one atom. Don't forget that for body face center, don't mix it up. For the body center, you just have one atom at the center. For the single centered unit cell, we don't have anyone at the center. We don't have any of them at the center. We just have the atoms positioned at the corners of each. And don't forget that I said that one of this is what is equal to what? 1 over 8, and then they are being shared. So 1 over 8 times 8, then plus 1 atom at the center is going to give us how many atoms? 2 atoms. Now, for this face centered, I explained that the atoms are positioned at each corners like the rest of them. But the difference between the rest and this is that we have one atom at the center of each faces. So how many faces do we have in the cube? We have 6. Now let me draw the diagram for you to see. So the atoms at the corners, this is the corner, this is the corner. So we now have one at the center of each. So we have this is top, this is the back, this side we are saying, this one at the bottom, then this. How many do we have now? We have 1, 2, 3, 4, 5, then 6. This one at this side, this side we're not seeing. So this is the top, this side we have 1, this side we have 1, at the bottom, this side we have 1, this side we have 1, and then the back also we have 1. That makes it 6. Now, so how are we going to do this calculation? So don't forget that I said that one of these is equal to 1 over 8, and then times 8, 1 over 8, times 8. The total at the corner is going to give me what? Then plus these ones at the center. So at the center we have, that is, each of them is representing half. That is half times 6. Let me mention again. One of this atom and at the face is equal to what? 1 over 2. Then that 1 over 2 times the whole at the center. You know, I told you that we have 6 faces, and then I told you that we have one atom is at the center of each faces. We have 6 faces, right? So we now have 1 over 2 times 6. It now gives us what? It gives us 6. So we have 1 here plus what? 3. It makes it 4 atoms. Make it 4 atoms per unit cell. Is it clear now? Now, this one has a higher packing efficiency compared to what? Body center. So I'm going to state here that it has a higher packing efficiency compared to BCC, to body centered. Now, let's take it a step further, or probably let me just draw this for better explanation. Let me just take 3 sides. Let me take the top, this side, and this side that we can see very well, so we can understand. So this is this top view we are seeing. We have this and this. Top. Now, on that side, we are having something like this. Okay, following. Then on the side, you have something like this and this. So, and then at the center also. For this one that at the middle, so I'm not able to draw this. So now, I hope it is clear enough. Now let's look at the applications and the implications of all this. I'm still considering crystalline and amorphous substances. So, application and implications. So, the applications and the implications. Now, let's begin with crystalline solids. Crystalline solids. Now, we have distinct properties of these solids that makes them suitable for various applications. Now, let's start with crystalline solids. For crystalline solids, materials like silicon are used in electronic devices due to their well-defined crystalline structure. Don't forget, I said that all this material, these crystalline structures, these crystalline materials, they have a well-organized structure. That is why we are using it in electronic devices. For instance, as I mentioned, silicon. E.g., silicon. And then another one is what? We have gallium arsenide. because of what? Because of its organized structure. That's why we're using it in electricity. And then for that of amorphous solids, now the first one we have is what? Is glasses. Glasses. Don't forget I mentioned earlier when I was setting the examples of amorphous solids, I mentioned glass and I mentioned plastic. So for glasses, which is an example, under amorphous solids, we have they are used in windows. Don't forget we are talking about the application and implication use in windows. We use them in containers and what? Plastic fibers. Another one is what? Is polymers. Polymers, we have plastics, and then plastic containers and medical devices. And then we have the last one, which is what? Amorphous metals. We have amorphous metals. For amorphous metals, these materials are used in application requiring strength and corrosion resistance. Used in materials requiring high strength and corrosion resistance. So once again, we have glass, we have polymers, we have amorphous metals. So don't forget that I said that for this amorphous substance, they vary. They vary in their structure. They are not organized. A lot of crystalline solids are what are organized. With this, we have come to the end of the video. Thank you. See you in the next class.